All right. Welcome everybody to this Signals and Systems course. I'm glad that many of you guys have preferred this course or the first lecture instead of the orientation. The orientation, I don't know when, but it would be starting this morning, maybe at 10 o'clock or something. But you are third year students, so do you need an orientation? I would ask. And of course, we all need an orientation for this kind of an online process. But last semester we were doing this, something similar to this one as well. So we are quite well aware of what's going on here. And what is going on at this point is, now that you are with this course, it is, oops, I have to open the pen. It's the EEM 301, Signals and Systems. Signals and Systems. Today we will make a jump start to Signals and Systems because that is something quite essential to make a jump start. This is the add and drop week. And for the add and drop week to work or function properly, you should be able to understand what the course is about, and consequently you may decide to drop it. Or if you haven't added to your elected courses yet, you may be entering the course and see what it is about and then decide to add it. And that's what an add drop week is. It is for courses. It's not for registration to the university. It's not a week for registration. Registration week was last week. Today, it's just an opportunity for you to decide, to better decide. So we will be doing the class, and those of you who may realize that the course level is not appropriate yet, for example, you may decide to drop. I'm not telling you to drop, but you may do that. So you have to know what it is about. What is this Signals and Systems thing? Well, it's a mandatory course. It's obligatory. So you have to take it in your undergraduate curriculum throughout the electrical and electronics engineering undergraduate. The reason is that this is the mathematics of everything that you can design and everything that you can analyze. So you can do two things. You can design and analyze. With what? You can design and analyze with the tools that you know. There are several tools that you are aware of and you will be aware of. And the most commonly known by you are probably the electrical circuits, for example, the passive elements that you have, the resistor, inductor, capacitor, or transistor and diode and things like that. Electronics equipment are also valid here, the wires, and the computer, of course. Those are the things that you design with, right? And some digital equipments are also available for you. And what are the signals that you analyze? The analysis signals that you are more familiar with are more like electrical signals, like voltages or currents in a circuit. But it could be a computer image, for example, a two-dimensional signal that you may want to analyze, a biomedical image, or speech signal, an audio signal. Those are the signals that you may think of. So usually you design systems and you analyze signals. This is a valid argument for any kind of an engineer. And most of the engineers, unfortunately, are not aware of that. They may be aware of it, but they don't care. The design and the analysis that we will be doing requires some mathematical formulations, some flavor of maths, particularly for linear ones. What is a linear system is an important issue over there. So without knowing the maths, some engineers may do a design according to the rules that they are aware of. They say that if you do this, then the output will be behaving like this and things like that. And the analysis is also similar to that. They say that if the observed function or signal or output data, it doesn't have to be a continuous function. The data of interest may, if it has these properties, then I will decide this one. That is an analysis, for example. But knowing the maths is important. And unfortunately, little by little, only the electrical engineers are dealing with these things. Previously, this was a fundamental concept of all engineering. So if you're a mechanical engineer, for example, you should be knowing signals and systems as well. Many of the research-wise working mechanical engineers actually do know signals and systems. But it used to be a mandatory course in the undergraduate level as well for computer engineers, for chemical engineers, industrial engineers. For example, for chemical engineers, the design of their system is by the chemical processes. So they have their chemical tools and some chemicals as well. So they pour some chemicals into the chemical tool and run the process. The process is the system then, and it has a mechanical way of working as well. You have started doing such system design in system dynamics course. Is there anyone here who haven't taken any system dynamics course, for example, here in this course? If you haven't, you may open your mic and say that, well, sir, I haven't taken that one yet. I will have to say that it is among a few courses that you should have taken. It helps, but it's not mandatory, but it helps a lot. System dynamics. System dynamics is briefly replaced by the third calculus, mathematics 3 course nowadays. So that also fits into the flavor. If you have taken that one, that's also fine. So that is one thing. Another thing, a circuit-related course like Introduction to Electrical Engineering, where you have seen the behavior of circuit elements, passive circuit elements at least. That you should be knowing. And differential equations is quite necessary as well, because differential equations are actually the representation of systems, for linear systems, of course. If you have a linear system, a differential equation mostly shows how it will behave. Otherwise, how do you state a system? How would you define a system? You can define a system by drawing a circuit, right? Because that is your system, the circuit. Or if it's something algorithmic, then you can also give me a software, and that software will be the system that runs according to an input, which will be data. It may be a file, or you may input some data to the computer algorithm and it runs. That is also a system. That's not a continuous system. It's we are going to call it a discrete system. But anyway, for all types of phenomena, it's very difficult for us to imagine anything which is neither a system nor a signal, you know? So for an engineer, I think the universe is composed of this, where we have an input signal, an output signal, and a system. Let's call it H. Sometimes input signals do not exist. the system just runs with respect to its initial conditions and just produces something without any kind of an input. But the output is always there. That is the observation. Without the output, without anything that you observe, you cannot really define a system. And here, H is your description of the system. You have to describe your system somehow. In many cases, this description can be a differential equation. But with this course, we will be starting some other systematic representations. For example, we will be saying something like an impulse response. That impulse response, dear friends, you may just mute your mics, okay? We can be hearing you. So impulse response is a way to represent a signal which is just a specific or particular response of the system to a particular input, and that input is an impulse. So we just perturb our system and observe how it behaves, and from that we will be seeing how the system can be represented. Impulse response, or it can be a frequency response. And this frequency response is like if the input has some kind of a frequency, if the input is an oscillatory signal, then how will it be delayed, shifted, or amplified describes the system. That's also a description. We will be seeing all these things throughout the concept of linear and time invariant systems. Maybe I should just extend this. Linear and time invariant systems. For nonlinear systems or for time varying systems, which are very awkward systems, most of the digital algorithms may be nonlinear. They may be time varying, not time invariant, but the mathematics for those things are very difficult. We have to start at some point. So we will start from linear and time invariant systems. And we will also, oops, what? Where am I? I guess here. All these things, we will find them to be equivalent. That is a surprise because they look very different. One of them is a differential equation, you know what a differential equation is. The other one is an impulse response, and the other one is a frequency response. But they are equivalent, and those of you who have taken differential equations courses know that they are equivalent, because the second two, this one and this one, particularly this one, is something that you have been using for solving differential equations, actually. So we are somehow trying to construct a differential equation, and we are solving it using the so-called frequency response. Did you know that? I don't know. But have you been using the Laplace variable of S in solving differential equations? The first derivative was notated by a single S times something. If it's a second derivative, we were putting it in S square. You remember that? That is essentially converting your differential equation to a frequency response expression. That S thing is essentially a frequency response representation. So knowing that will now help us to interpret the differential equation, not in terms of a differential equation only, but in terms of a system, that now we have a system. And systems have responses. According to the input, they produce the response. If you input an impulse, if you just perturb it abruptly, then the response will be an impulse response. Or if the input is a sinusoidal oscillatory signal, then the output will be the frequency response of that particular frequency. But you can change the frequency and you can observe how the system behaves. So they are the same things. We will see some examples. We will start seeing some examples. But at the end of the course, you will be seeing all these things, the differential equation, the impulse response, and the frequency response for continuous and discrete signals. Now, let me briefly mention about what do we mean by continuous time. Signals and continuous time systems which act upon those signals versus discrete time. The continuous time signals or continuous time systems are functions of time or functions of a single variable like x of t or f of t, right? These are functions of time. This t over there, we will be calling it time throughout the course. We'll just, for the sake of easiness, we will just call it time. But it doesn't have to be time. For example, it can be a measurement along the space. So it can be actually, for example, the distance. So it doesn't have to be really time. But as you see, we are saying continuous time. Well, it's just a notation. We don't get stuck with that one. Sometimes signals are not time signals. But if it is continuously changing, then it's a continuous time signal, like x of t and y, f of t or y of t or whatever. And notice that we are using the parentheses for putting the argument into the function, like y of t, okay, in a parentheses, normal parentheses. That notation is critical because I usually indicate it in the first lecture now, not in any later. So for those of you who did not attend this course, will not know it. I hope you're just communicating with one another. You can just make some groups on the social media and try to make a forum. Sometimes if you need some assistance, I can also provide in the Canvas system, Mergen, a discussion forum where you can just communicate quite freely, okay? That will be a democratic discussion forum. By saying democratic, it doesn't mean that you can just say anything. In the democracies, you cannot insult one another, you cannot swear to one another, and you cannot be irrelevant to one another. But otherwise, it would be quite democratic. If you have an idea, you can just discuss and ask questions. But, so this notation is critical. Please tell your friends that the professor is very strict about that one. So if you are talking about the discrete time signal, which I will show now, and still notate it like this with parentheses and put a t inside it, I just hate it. Okay, I just hate. The continuous time variables are like t, and there are some other things that are also available as variables, as parameters. A discrete time signal, on the other hand, is notated with a square bracket, like this. And inside it, we usually put some index variables. And index variables are mostly K, L, M, N, right? Those 4 letters are indices, used for indices. I don't expect x of k with k to be a continuous variable, as if saying x of t in a normal parentheses. That would be very bad. Or f of k, or f of n, and g of m. These are like discrete time examples. Please stick to the notations, okay? Don't write or try to draw a discrete time signal with normal parentheses, and don't try to say that a continuous time signal is notated with a square bracket. And how are we going to draw them? By the way, the number of variables inside the parentheses or square brackets determines the dimension of the signal. How many dimensional signals are these? These examples are one-dimensional signals because there is only one variable inside the argument list of a parentheses. X of t. X of t is a one-dimensional signal. X of n is a one-dimensional discrete time signal. If you put more than one variable, like, for example, come on, what is this? For example, like x of t1 comma t2. For example, this is a two-dimensional signal. It's a two-dimensional continuous signal. We're not very much familiar with two-dimensional continuous signals. Actually, they correspond to continuously varying surfaces. Okay? That is two-dimensional and continuous time. We are more familiar with two-dimensional discrete time signals, like x of n comma m, for example. This is also two-dimensional, and it's discrete time. For example, a digital image. What we are streaming right now to your computers is a discrete time signal, a discrete time two-dimensional signal, which is a digital image. So these are continuous and discrete time versions of signals. And we will be dealing with continuous time and discrete time systems that are connecting continuous time and discrete time signals. Like if it's a continuous time system that enters to a system and the output is a continuous time signal like this, for a linear and time invariant only, we will discuss about this a lot throughout this course. We are going to indicate it like this: h of t is the system. And h of t is a particular responsive behavior of the system. You don't have to care much about it. But it is a continuous time system. And it may be like x of n going into a system and the output is y of n, which is the response of the discrete time system to the discrete time signal input x of n. And the system will be noted by h of n. So h is the keyword here. It's the key letter. We are going to be representing systems with an h mostly. So try not to use h as a signal name, okay? H of n is the input to a system. What? H is a system. Okay, be careful about those things. Now, let's try to talk about at least a few properties of the signals, and then we are going to give a break. And the break will be like 10 minutes or something. Or let's make it 15 minutes. So after half an hour of a lecture, we are going to give a 15 minutes of break. And then, or it may be 20 minutes of lecture. It may be sometimes longer. I'm sorry about that. I don't want to make very long lectures, but sometimes it's necessary just to keep everything within one concept. Normally we have 2 lecture hours, and those lecture hours are like 50 minutes. So we have 100 minutes. Instead of that, we will be doing maybe 3 half an hour lectures, something like that. Anyway, now some signal properties is the thing that I want to start talking about. We have a lot of signal properties, and those properties are necessary for the analysis. If you know that the signal has this kind of a property, you will analyze it accordingly. But of course, you have to detect that property of the signal. Some of them are quite obvious, of course. For example, it can be continuous time and discrete time. And meanwhile, I'm showing you the abbreviation of continuous time, which is CT. and the discrete time is dt. So in an exam question or something like that, it would be ct and dt. That is a clear definition. Another property may be an even signal and an odd signal. An even signal has x of t is equal to x of minus t. That's a symmetric signal. And the other version is an odd signal, is an antisymmetric. So x of t is minus of x of minus t, like this. So for example, a cosine t is an even signal, but a sine t is an odd signal. Of course, it may be, your signal may contain both. It doesn't have to be either even or odd signal. It can be periodic or aperiodic. That's clear, I guess. If it is repeating itself, then it's periodic. But the periodicity is a difficult definition. It must be periodic from time minus infinity to plus infinity. Everywhere it must be periodic. So within a period, from a starting point, if it is periodic and then it ends or it continues, for example, we cannot call it a periodic signal because it is starting here. And when you shift something, when you shift it by an amount, it will not be the same signal. But for periodic signals, if you shift by the period, that would be exactly the same signal. So periodic signals are infinite extent, actually. It may be random signal or a deterministic signal. Of course, we will be dealing with deterministic signals. We have to first know the methods to analyze them. But after a while, it will be regarding random signals for telecommunications, for example. Okay, they will be random signal processing, mostly. There are some other types that I can think of, like a power signal versus an energy signal. I will have to explain these in a little bit more detail, but after the break. So let's stop at this point. I will end the meeting right now. Within a minute. What time is it? It is 9:30. We are going to meet at 9:45 again. Okay, and we will continue from there. So don't go anywhere. Don't go to the orientation or anything. Okay, that's not necessary for you. You are third-year students. You don't need orientations. You need more of this thing because you will be responsible in the examinations. In the exams, no one's gonna ask you questions from the orientation, but I'm gonna ask you questions from this course. So I will be waiting for you. And the second hour is a little bit more critical because I will continue by giving you some more information about textbook, about how we are going to do the exams, how about the homeworks, what about the projects and things like that. I deliberately did not explain those things in the first hour because in the first hour I want to talk about what is a signal and what is a system. First things first. So I will stop at this point and I will be waiting for you at 9:45 at the same address. Okay, see you until then.